as usual, welcome. And what should we do? Today, I want to say something about the third construction that I promised, right? I said that we have three, at least I want to present three ways to construct toposes. One was the sheaf one, the other was the H-valued version. In the second construction, we actually used it for some independence, for continuum hypothesis, for instance, and the independence of the pigeonhole principle. And today I want to do kind of the opposite. So first I want to present something a bit elementary, prove some independence, but this time the independence would be just for constructive arithmetic, if you like. And but then I use that kind of intuition to construct the third topos, right? And yes. Okay. So what should we do?
Please focus.
Is there a
Yes, thanks.
is there a lecture next week?
Yes, that's a very good question. Should we have one lecture next week or not?
Otherwise, this is the last lecture.
Not really. But that's another thing that I have to say. But should we or shouldn't? It is 23rd, right, of December, I guess, which is technically, yes, but technically available, I don't know. So just
I won't be here in person.
you won't be here in person, but online could be. Okay. So, okay, what about you, Neil? You asked, so then.
I did. I didn't realize it was already the 23rd next week. I could be here.
You could be here. What about you, Pavel?
In principle, I can attend at least remotely, but I cannot promise for sure.
Yeah, actually, I don't know if anyone will be able to give us the key to the office and so on.
But okay.
So if there's no seminar next week, are we finishing today?
No. Okay. So there are two things. One is that, of course, I'm not finished, and I could not finish today. The bad thing, and we have it on record. The bad thing is that I leave Prague next year, so in January the 2nd. So therefore, it seems that we couldn't just, complete the thing. But that would be just very bad. So what I can do, and I'm sure that Neil doesn't like it, is that we can have some online, the same thing, seminar, but for 2-3 probably at most, I promise. And then I can just finish the whole thing.
I would say one.
No, of course, it cannot. I have to insist at least 3. But you bear with me for 1 year, so you can do for 1 week. Right? Yeah. So then I don't know what should we do really next week. So you say that probably.
I can find. It's possible the place will be shut. Basically, nobody knows.
Okay, the best. Okay, so let's say that we don't know now, and then I send an email. Either I say that we have it or we don't. Yeah, so we will see.
If you ask by Friday, then people will know whether they will be able to attend.
Yeah, we will do.
It's in the construction last time.
Mm-hmm.
This nice thing that this density condition turns into this forcing. No, sorry, the density condition and forcing arises from this double negative thing.
Exactly.
So if you don't have this double negation, you get some unprovability and some intuitionistic logic.
Essentially, yes.
And does this correspond to something in forcing?
I don't know. So the point is that usually people don't use forcing really for constructive things, right? Forcing as forcing is just something for classical set theory, right? Of course, we can do it, and the only thing that you have to do is just forget about the double negation part. But usually they don't do anything of that sort. Probably. Oh, okay. Yes, there is some. Yeah, this takes the literature on kind of forcing for constructive set theory, but it is just kind of identical. Just forget double negation, right? So there is no correspondence that I can mention. Really. Okay. So any other question? If not, then let me go for what I promised. Today, I want to talk about something that's called realizability. Right? And the idea is the following philosophical kind of thing. So you know that I said that topos theory is the categorical version, a more generalized blah blah thing for set theory, right? So we actually constructed somehow the axioms of toposes from looking inside the category of sets, right? And then incidentally, we saw that actually the logic is intuitionistic, meaning that the sub-object of anything is a Heyting algebra, not necessarily Boolean algebra. And therefore, we can say that we have some sort of intuitionistic set theory, right? Constructive set theory. Because it is set theory, but the logic is not classical, it is at least constructive, so why not, right? It is the categorical version of constructive set theory. There are also more natural, like ZF style, that you change logic to constructive logic, change a bit of the axioms, etc. But the point is that if you come from more philosophical point of view, you would ask yourself that what is a constructive set, right? That we are formalizing here in topos theory. And that, to answer that, you have to know something about constructivism as a philosophy, right? It is some sort of standpoint in the foundation of mathematics, and more or less it says that everything should be constructed in some vague sense, right? So either you are working with some objects, numbers, real numbers, whatever, right? You have to construct them, one. Two, or you are working with propositions and you claim something and then you have to prove them, right? And proof means, again, something, informal. You have to find the proof for them. And since you are constructing things in your philosophy, it is time sensitive, right? So it's not like the usual classical mathematics that it is timeless, right? So you are doing your constructions in time. Therefore, it is possible that I have a construction of something tomorrow, but not today, right? Probably I prove something tomorrow, but not today. So it matters, right? The time also matters. Huh? Why? In what sense you don't believe me? I'm describing some philosophical standpoint somewhere, right? So, yeah, probably you have to say that you don't believe them because the philosophy is not, coherent in some sense, right? Do you say that?
I think I need to see the format.
Oh God, no. So this is the informal point of view. And then to formalize that, so you have to, of course, say that what is a construction and how it is time sensitive, right? So, okay, forget about construction for a moment. And for time, we had some sort of formalization, right? So if I want some sort of constructive set theory where everything can change over time, then we saw that we had this set to the C, for instance, characterization, right? That C is the category of time, everything changes over time, and then these are variable sets, therefore constructive set, whatever it is, could be variable, right? Also for the H-valued setting, so this is the sheaf setting, the pre-sheaf setting actually, we had also the H setting. So assume that my H, the Heyting algebra, the complete Heyting algebra, is just the offsets of some poset. Think of the poset as time again. And then if you remember, H set simply means that, so the category of H sets, everything, the value is something in H. It is some offset here. So the value here is not just true, false. It is all the points of time, all the moments where the thing is true or constructed, right? It is also time sensitive. You don't just say that it is true or false. You pick all the points where it is true, right? This is just the best refined version and pick them. So we had the time version. The problem is that, but both of them are just the usual set theory, but we, allow some sort of time. And that's it. We have no construction, really. The main thing is construction, but there's no construction. So what do we mean really by construction? Then nobody knows. It is some sort of vague, informal idea. But the first kind of attempt to formalize this construction, as Neil likes, is this realizability by Chiellini. So the guy came up with the idea that forget about anything that I said about topos theory or whatever, right? Category. And we are just now in the beautiful, simple lands of logic. And for Chiellini, everything lives in the language of arithmetic, meaning that you have zero, you have successor plus times, and probably it is the only thing, and you have just equality as your atom and nothing else, I guess. And then you can write propositions, right? So you write just the usual propositions like a sentence A. So A is just a sentence, any sentence, but it is a sentence. It's not a formula, right? There is no free variable. And then what do I mean really by a construction of A, right? So that's Chiellini's idea. So whatever construction is just a finitary thing, right? Therefore, I can code it with numbers. So therefore, I have to say that when some number R is a construction, this time, this force stands for construction, R number is a construction for A. You can read it as a proof of A, some sort of proof, not proof in the usual way that it is just a sequence of formulas or whatever, right? So what do I mean by that? So first I have to define this guy, of course, recursively on A, right? So what is when I have conjunction, disjunction, blah blah. So just forget about the atoms first, and let me just start here at the second level with this. So what should be a proof of conjunction or construction of conjunction, really? That's a matter that I have to define. And actually Chiellini does it, right? So, no?
So which one you construct first?
Which one I have to construct first? What do you mean? Which one between? Huh?
But I don't, a construction of both, one construction.
Ah, you mean time?
Yeah.
Okay, yes. That's good. But the point is that now I just forget about time. I do just my construction, and it is possible to do both at the same time. But then I'm sure that you kill me. So, so let's just do just pure construction. So, timeless construction, but construction of A and B should be what? For A and B, right? And as everything is a number, so just think that it is just the codes of pair, right? So and therefore I would say that R should be, as you said, a tuple R0 R1 such that R0 is a construction for A and R1 is for B. And what happens for A or B, right? So what's the construction for disjunction then? Of course, it should be a construction of one of them, right? But so here you can choose many different things, but the basic version that Chiellini came up with is that you have to also know which one you are proving, really. And therefore, R again is a pair but this time either R0 is 0, which means that I'm the first, and then R1 forces A, or R0 is not 0 or it is 1, doesn't matter, and R1 forces B. So I have a pair, I read the first guy and I know which one I'm proving, and the second guy is really the proof, right? Okay, fair enough. And what happens for implication then? For implication, what is a proof of implication? Should be the proof of implication. Think constructively, right? Whatever. As a construction, if I come up with the construction for A plus B, it should be a machine. Exactly. And but everything is a number. So therefore, it's a code of a Turing machine that does that. And actually, it is kind of good because it should be a Turing machine, right? It should be something accessible, describable by a human being. So therefore, you say that for any, say, I don't know, S, such that S forces A, then, or I have to say this, first R, so this means that R is a code of a Turing machine applied on S, right? And this guy should exist because not all functions are total, right? It could be a partial function. So the algorithm holds, and it says that I am a proof of B, right? Should be a proof of B. So remember this notation, that's very important that I have, right? The dot importation, the dot notation. And what happens to there exists X, A of X? So a construction for existential thing, that's very, very constructive thing, right? So you have to first construct X and then a proof that A of that X really is constructible, right? So therefore the construction should be again a pair, but this, okay, not like this. So N and R1 such that R1 is the proof of A of N. So if I have the construction, I can read from it the witness really, and also the proof of the witness. And the last one probably is at for all X, and like implication, for all should be also a machine that reads N and construct the proof of it, right? So therefore, R again is a code, this time for any N, R dot N halt, and R dot N is the proof of A of N. So it's a machine that transforms any N to a proof of the index. And also, of course, it's total this time. Is fair, right? So now let's come back to the atoms. The atom, but there is no proof of but. Of course, that's contradiction, right? There should not be any proof of but, just by definition. And what happens for this? A proof of some equality between two terms, because this is the only thing that I have in my language as atom, is equivalent to real equality. Remember that it's a sentence, therefore it is just equality between two real numbers. I mean natural numbers, right? It could be 5, 10, I don't know, whatever. If they are equal, everything is a witness. If it is not, then nothing is a witness, right? So here I'm more or less saying that I have no, real construction. You can choose again something like, I don't know, the T itself is the proof, right? That you are doing really the computation and showing that they are equal, but whatever. So this is the usual one, right? Okay, so now if I give you a sentence, whatever it is, you can come up sometimes, of course, with a realizer, right? So this guy is called a realizer for the formula, or as I call it now, a construction. So construction is kind of informal term. Realizer is the formal term for this guy or their variants. So, for instance, example. The example says that, so do you have any, okay, apart from the atom, do you have any example, pure logical example, something that I can say that it is realizable? And you can come up with some realizer for it. So some sentence such that you know that there is a realizer for it. Yes, yes.
It's taking place in a standard model.
Yes, yes. Yeah. It could be more generalized, but I don't care for now. Right? So some sentence. Of course, you know, for atoms, there's some obvious ones, right? I can write, I don't know, 1 plus, you know, whatever. So successor of 1 plus 1 is successor of 0 or something, right? These are true, therefore they are realizable. So these are not interesting. But something more, like something logical. Let's say,
A implies A.
yes, A implies A. A implies A. What is the realizer? There could be many realizers, right? What is a realizer? Say, yes. So any code for identity works, and sometimes people write like this. It's not really true, but you know, it's a function, but any code of it. You can also formalize it in a way that it actually completes the things. So also more than that. So probably you have this, right? So it should be the code of the function, which is projection, right? And also the other one. Or you have this. It is the function that maps any element to 0 and that element, right? And the same for B. And to give you more examples, probably I have to define something. So let's say that I have now 2 formulas. So what do I mean by this? Right? So what I define is realizability for just one sentence, right? Now I want to do 2 things. One, probably I have some variables. 2, one implies the other, right? In the realizability sense. So what should be the natural definition here? It should be a function, right? Or a recursive code or whatever, right? Such that for any n, and for any proof here, it transforms it to a proof there. So this simply means the existence of some, you know, code, if you like, such that for any n bar and any s, if s do this, then r dot, say, the pair of n bar and s or whatever forces b. So simply you can transform any realization of this to that via a recursive function in a uniform way, right?
That's the same as your quantifier.
Yes, yes. So this should be more or less equivalent to this, right? So that's the definition because it is just better behaved. But probably one exercise would be okay. So I will say. We will see. So I have to put it here and change my board, please. Yes. So, yeah, I define that just to have more, you know, wiggle room somehow to define more examples. So, for instance, you can see this. Another example would be this, that if you have, say, AX forces BX and CX, say, and, okay, I have to do something easier first, right? So CX, BX, then my CX forces AX and BX. So the usual rule for AND, right? And that's the case, right? It is kind of obvious that I have some recursive function that reads X, reads the proof here, transform it here. Another one, make the pair of them. Then that guy is still a function, recursive, etc., that reads X and C and computes this, right? So more or less what I'm saying is that pairing is a computable function, right? Nothing more, really. And you can do kind of the same like this, that if you have AX, CX, and BX, CX, then it implies that AX or BX, right? Why? Because I have two maps, reading X and reading a proof here, transform it to C or B. And if you read something here, then you have the first guy that decides whether you are proving A or B. You read that. Based on that, you call this function or that function, right? So that it is now important that the first guy says which one, because otherwise I have to check the realizability of something, and it's not that easy, right? But now I have the first one, so I know which one I have to. So what I'm saying is that the case function is computable. So these are just very easy, right? But something not a bit non-trivial, so probably that is the first guy, this is the second guy. The third guy is this, that if you have CX forces AX and CX forces AX implies BX, then I have CX implies BX. So that's modus ponens, right? So how do I know that? Really? So of course, whenever I have some implication or universal quantifier, things are a bit more complicated because you have to work with the codes, etc. So what I'm saying is this, that you read something and then you compute in a computable way a code here, a realizer here, a realizer there. And how to construct a realizer for B? By definition, a realizer here is a machine that transforms any realizer to any realizer, right? So I have to just apply this machine on that guy. This is the only thing that I have to do. So what I'm saying is this, actually. So cases, pair and case are computable. Here I'm saying that there is a universal machine. A machine that reads the first guy, right? So this is this is also a computable machine that reads E, reads N, and then computes E dot N, right? This is what I'm saying.
You're saying, so I can see the fact that universal machine exists is useful for proving.
Yes.
But you're saying the con does also help.
I'm not saying really that, but it seems that I have no other way to do it, right? To apply this to that, right? So just vaguely, informally, the only thing that you know here is just it's a machine that transforms a proof to a proof, right? You know nothing else. And you have another proof, right? So the only, roughly speaking, the only, it's not a formal thing. Roughly speaking, the only way to do it is that. But it is, if you change your language from arithmetic to something more free, then it is possible even to prove it, really. But now I'm just, you know. So, and probably I have to also say this, that what if CX and AX proves BX, then your Cx proves Ax implies Bx. Okay? So how do I know that? So here what I have is a machine that transforms a pair to something here, right? So the thing that you have to do is just to fix this guy, read this guy, and then transform it to a function that reads the second and transform this, right? This is just the carrying, the usual thing. So first you believe it or not?
Well, I don't understand why so this notation with the forces involved.
Yes.
It's the same as using universal quantifier multiplication,
Yes.
but it looks more arbitrary this way, because I'm sure you could write equivalent things, putting that sign in different places. So I don't understand why would you put it rather than stick with it.
Okay, for instance, how do you do something arbitrary here, really? Because I'm not, everything is forced upon you, right?
Well, it's everywhere. So this sign says there is a R.
Yeah.
That forces the universal indication.
Yes, yes, yes.
Oh, you mean how would you express it differently with the symbol? Oh, I guess I don't know. I'm just wondering why I'm writing this. You're saying it's just you try and do it otherwise is actually the simplest way to express it.
It depends. So, for instance, let's say that I want to prove soundness, some sort of soundness for logic, as you can see, right? So either you do it with the Hilbert style thing, and that one would be good. But this one is more natural for your natural style deduction.
It's more like a secret.
Yes, but they're equivalent. Okay, so you believe this, right? That what I'm saying here is that the universal machine is computable. Here I'm saying that SMN theorem that probably you see it in recursion theory. The theorem simply says that if you have something of like F, I have to write it here. So if you have a function computable with two arguments, then you can simply write it as reading one argument first and the second via some code. So there is some E such that E applies. Okay, so probably I have to be careful here. You can write it as G of some whatever. That's easier for me, so I do it. So there is some computable G that does this, right? You can read the first and then apply it on the second, right? So more or less what I'm saying is that read it as a variable, right? And then fm variable is a computable function, and you can find the code for it. So that's it. But that finding is also something, computable that I'm not saying here. But anyway, so this is exactly the idea here, right? So lesson number 1. Is there any reason that I'm using all computable power? You can use probably feasible computation or something. Or even more. Who says that it should be just real Turing style computation? Whatever computation, more generalized, right? More powerful, with some Turing degrees. I don't know, whatever. Some continuous functions, I don't know. As long as you can have that universality and that SMN, and the rest is just the case, etc., the pairing, some basics, you can do it. There's no reason to use all the recursive functions. But you cannot use the feasible things or something of that sort, simply because there is no universal machine there. It should be a feasible function that's universal for all feasible functions. That doesn't work, right? But as long as you have these basics, and it is just usual for any, kind of generalized recursion theory or whatever, you have. So, okay. And if you are interested in feasible style of thinking, then you see that what you lose, everything is there. SMN is also there, but this is not there. So in the logical point of view, you lose your modus ponens if you work with feasible things. And that's a serious problem in the logical realm. Anyway, so The same is kind of true. I'm not saying it, right? But you know that you have also the trivial things for quantifiers. Like if I prove for all, then I can apply it, or I can just introduce universal quantifier or something of that sort. And so probably I can now say these examples, the soundness theorem, right? Soundness. Simply, it says that if something is provable in Heyting arithmetic, what is it? It is just piano arithmetic with constructive logic, with intuitionistic logic. Then it is realizable. So this notation simply means that there exists some R that realizes A, right? For any sentence A.
Soundness of, I think.
Yes, yes. So how to prove it? I already did my logic part, right? More or less. This is just the usual intuitionistic kind of argument for all the, connectives. The only thing that I have to do is just the axioms of HA and probably the obvious axioms plus the induction, right? The obvious axioms are always true because they are just something universal, right? They are something of this sort that, I don't know, S, X, X plus 0 is X, right? These are some things like this, right? And these are realizable simply because why? Because, to realize this, I have to come up with some R such that R dot n for any n is a realizer for n plus 0 equals to n, which is true. And therefore, everything is a realizer of it because it is atom. So just pick some R as some constant function that reads n and answers 0 or something. Who cares? So these universal things are easy. What is not that easy, but probably not that hard, is induction. So if I want to prove induction, then I have something like this, right? Or any other equivalent version of it. So how to realize this? How to realize this?
You realize the things on the, realizer of the things on the left.
Yes.
That particular gives you a realizer of the things on the middle. So this lets you construct realizers for AX step by step, just as a sequence.
For any n, right? And then the whole thing is a constructive thing, therefore it is like obvious. So you can see, right? So if you have a realizer here, you have two realizers. You have a realizer R0, say for A0, and you have R, so now S, say, for this guy. And then our task is to find a realizer here, meaning that probably I have to come up with some F such that F of n realizes A of n, right? For any n. And F should be computable. So of course, I start here, I apply this S on n, and on the previous one to get the next one, right? So this F should be then defined like F of 0 is R0, F of n plus 1 should be simply S applied on n, applied on F of n, right? And then you can get your function. But note that the whole thing also should be computable. Because I'm not saying that if you have a realizer here, you can construct a realizer there. I'm saying that the whole process of constructing a realizer here from that is also computable, right? But that should be checked via that SMN thing and tricks. Yeah, you have to do everything code-wise, etc. Right? But the whole thing that I'm saying is simply not that if you start with a function, computable, and some element, you can iterate it on that. I'm saying that the act of iteration is also computable, right? Which is the case. So you have this guy, fair enough. Now what I have to do, the point is more or less they are the same if you promise to work with some lower complexity. So for instance, let's say that A is just exists something and something constant free. Then the witnessing actually does find the witness for X and nothing else. The rest doesn't matter because it is just easy. And the rest is also easy for me because it is everything, you can just transform everything because it's classical to something basic. And the existence is this guy, right? Where are you? And this one. So more or less, I'm finding this N. Yes. And also here. So as long as you have some existence and nothing else, there's no quantifier, they are the same kind of. So you can read this as the generalization of witnessing to all possible things, all possible, universal quantifier or any combination of them or whatever. But then the price that you have to pay is that you have to go for intuitionistic. Because of course I cannot, as we will see,
Well,
I cannot
you're saying
realize
if we're only
completely.
working in this week, it's
Yes.
the same as this. But you have to introduce it.
Somehow.
So
So
the intuition comes in. What is wrong.
yes, but also for the lower level, it is still intuitionistic. But the point is that you can harness that intuition. It can be classical, but you have to do some tricks. So the point is that the machine that I have cannot realize excluded middle. But if excluded middle is just so weak, like transfer free, for instance, then I can do it. And then I can handle your witnessing with just existential quantifiers.
Well, okay, I don't really get it.
Okay. I also have some conjecture, actually, historical conjecture. The historical conjecture would be, this is from 1945 or something, and witnessing came very late, right? So I have some sort of conjecture, but probably Paul can prove or disprove it, I don't know, that kind of witnessing is inspired by this. Whenever you have, lower complexity, then you can do everything classically. But I don't know. So okay, now, do I need this? I'm sure that you know the definition, right? So there's no need to keep it, I guess. So then what? Then now we saw many, because we have soundness and we saw some logical things. At least we know some realizability, right? That we know that something you can realize. But probably it is also good to see some unrealizability and then use it to prove independence from HA, right? Because if I prove something is not realizable, then I can prove that it's not provable. And this is some sort of, finding a model, right? I'm constructing a weird model using codes and etc. But it is a semantics for HA in that sense. It is at least sound, and it won't be complete. But soundness is enough to prove independence, right? If I want to prove that HA cannot prove something, it is just enough to prove that it is not realizable, right? So therefore, it is reasonable to work or try at least to prove some non-realizability. So first lemma, very ridiculous lemma that says that for any sentence A, these two guys are equivalent. Negation of A for sentence A. That is sentence. So that's very important. So one way is always true. simply it says that if you can realize negation A, of course you cannot realize A also, right? Because if you do realize both, I can apply the realizer here. Negation A is A implies but, right? It is implication. It's a machine. You apply on the code of A, and you get a realizer for but that is impossible by definition. So one way is obvious. So you cannot realize both, right? Like you cannot prove both because it is inconsistent. But the important thing is just the converse. So meaning that if I have this, I can really realize negation of it. But this is not very interesting. So the whole point is that what is a realizer here? It's a machine that transforms proofs of A or realizers of A to realizer of but. So if there is no realizer for A, I can use whatever I want, right? Who cares? It could be a code of any machine because you cannot apply it on any proof of A, and therefore, trivially it is transforming proofs of A, realizers of A to realizers of but. So you have this.
Sorry, when you were defining a realizer,
Yeah.
you gave a series of conditions.
Yes.
You didn't specify any particular realizer.
No,
So,
because yeah.
Is that significant? Or
I-
is there some fixed one?
No, they are not. So the point is that I'm defining the family of realizers.
You have to show the family is non-empty, right?
For some, it is empty, like but, for instance. For some, it is not empty, like A implies A.
No, but in general, you're saying you're defining the family of codes that are.
Yes,
Yeah.
family of numbers that realize A, that is defined really.
Right, you wrote this condition that nothing is a realizer, there's no realizer of the false.
Yes.
So, not sure what the status of that possible definition is.
So it simply says that these are one of the atoms that you have, right? So I'm free to choose my realizers for them. I
Well,
choose
no,
nothing.
This relation.
Yes. Yes.
Is it some definite thing?
Yes.
Then
So you are defining it recursively, right? For any atom, you know what are your realizers and what are not realizers, right? And also for conjunction, you know exactly they are pairs of realizer of that and that. So it is determined. Also for disjunction, implication, etc. So it is really recursively defined. So the whole set
so
is
particular-
defined.
there's no question about whether it's consistent or not, because it really is recursively defined.
Yes.
It's guaranteed.
Yes.
All right.
Yes. But could be some nonsensical thing that you define, but we will see that it is not. It's not. So you have this property, 1, 2. This is non-trivial lemma. Probably I can call it the truth lemma or something of that sort. So it says that, okay, first definition, formula A is called existence free if it has no occurrence of also existence and also discharge. So you have nothing of these two inside your formula, right? It's E-free or probably sometimes people call it almost negative, right? Because negative means negation of something, but these are kind of almost negative. But whatever. So that's my definition, right?
Negation.
Yes, and implication also. But just don't use these. Of course, you can use some of them and prove that they are equivalent intuitionistically to something universal, like negation of existence is equivalent to universal, but I don't care. So this is a very syntactical thing. Just don't use it. And then the theorem is this. So our lemma is this. 1, so A is E-free. And probably I have to be precise, that is a formula which is E-free. And then if it is realizable, should I write it like this? Whatever. So any instance, if it is realizable, realizable, then it is also true. So that's a connection between realization and truth for E3 formulas. Two, the converse says more. So what I'm trying to write is the converse, but something more refined. So there exists some code, say R index A, and it is independent of n, so it is just one number, such that for any n, if this guy is true, I hope what I'm saying is right, really, probably. Then what? Then RA realizes AN. So what I'm saying is that if the guy is true, regardless of n, I can realize it with one fixed number, right? There is a canonical choice that good. That always you can say that if the guy is true, then you can realize.
So I don't understand why. This is
This n, let's say that this is standard model. It's calligraphic n. Yeah. Okay, is it clear what I'm saying? One is clear. I'm saying that if your E3 formula is realizable, then it's true. The second, I'm saying that if it is true, then it is realizable. But more than that, the realizer is something that you can construct just looking into the construction of A, the formula A, and it is also independent of natural number n. Yes. Have some rescue mission now. Because yes. This is the choice between slow but constant noise, right? and something big but just sharp. I also prepared a second. Yes, so okay. So do you see what I mean, right? So this is just the clay, right? If it is true, then there is a realizer. It's just a converse of the first. But my point is that the realizer is something independent of it. Can be chosen as something unique. So how to prove it? By induction on n, by IA. Sorry. By induction on A. So the point is that, and at the same time, of course. So for atom, this one is obvious, right? Because it's just the definition, right? You say that two things are one equality is realizable if and only if it's true. And you don't care about the realizer, and therefore here I can just pick some constant number, right? I don't care about n or whatever. I can just pick 1, 2, 0, whatever. And then this conjunction is easy. Disjunction I have none in my formula, and universal and implication are the main things. And probably I have to show just implication, and you believe me that the other is also true. So for one, you say that. So if I have implication, then I can see that the interaction somehow. So let's say that this guy is realized, right? Some implication. And then I want to prove that it is true. So to show that it is true, I also assume that A of n is true, right? And 2 says that since it is true, I can use that uniform realizer that says that RA is a realizer of A of n. Then I have some realization here, S, I don't know whatever it is, so I don't care then. I apply it, I get some SRA as a realizer for Bn, and now I use the first that if something is realizable, then it is true. Right? That is the easier one. The harder one kind of is this, and the proof should be that I have to come up with a uniform realizer for implication. because that's my, task to define R of A for any A. And that uniform thing that I have to pick is simply easy. So pick R A implies B as the constant function that reads anything, but just always says RB. Don't care about A, right? And I have to show that it works. So let's say that N is a model of AN implies BN. And I have to show that this guy, R A implies B, realizes the guy. So how to prove it? So to show the realizability, I have to pick some realizer here. So some S as a realizer of AN. And my task is to show that this applies on S, which is just RB, right? I have to show this, that RB, because I don't care about S, because I don't care here, right? It should be a realizer of B, right? So now what I use is this. S is a realizer of A, right? Therefore, A is true, like the first guy. And therefore, B is true. And since B is true, the second guy says that RB is a proof of. Okay? So that's just a, something tedious to write. But the point is that if I use disjunction or existential quantifier, there is serious difference between the two, right? Because more or less the idea is that something could be true, right? So some existence could be true, but then you cannot find the existential quantifier really in a recursive way, right? It could be possible, right? But anyway, you have this guy, and then I can use it to prove some unrealizability. So, for instance, I don't know, some corollary, there exists a formula A such that this guy is not realizable. So excluded middle for formulas is not realizable. I'm not saying that it is not realizable in any case, because of course A could be top or whatever, right? But I'm saying that there is at least some instance such that it is not realized. Any idea what A should be? We can just find A somehow, right? Let's say that we have some A, and let's say that we have this some realization of this guy. Then what is the information that I get from the realizer? By definition, I get a machine, computable, that if I apply it on N, I find a realizer here. Which means that the first guy says that either I'm realizer here or there. And if I promise that I choose my A E-free, existence free, then the existence of realizer means truth. Therefore, what I'm saying is that there is some computable function that reads N, decides whether AN is true or false. That's too much. Because in arithmetic, you can write some A's, like halting, for instance, that is undecidable. It simply says that if it is true, any definable thing, any E-free definable thing should be decidable, which is not the case. Not really. So there is a trick. So the thing is, yes. So first you work with non-halting, not halting, and then it is E-free. But then you have double negation here, but it is fine when everything is a sentence. So there is some tricks, but yes, right? So what I'm saying is that the realizability thing that everything should be decidable, kinda, and of course there are some non-decidable things. The other is this, that there exists formula B such that if I write, such that this guy is not realizable. What should it be? It should be, I guess, this. So that's a classical thing. The second guy that I'm writing down is also a classical thing. And these two classical things are not realizable, right? So that's of course classical, right? Double negation is just nothing in classical, and then you have so that the first is excluded immediate. The second is called double negation shift because you can shift it. It is also not available in intuitionistic logic. So what I'm saying is that it is not realizable, and this time the trick is that you use B as A of X or negation A of X, and A is the first guy in the first corollary that we have, right? So let's say that this guy with that choice of B is realizable. Then the point is that double negation of this guy is always provable in intuitionistic logic. So this guy is provable and therefore realizable. If the whole thing is realizable, I can realize this. I can realize double negation for all this. So therefore, I can realize double negation of this. Right? But realizing double negation means just realizing the thing itself. Why? Because we had this lemma. Right? So this lemma says that negation is just nothing, right? So therefore, if I have negation A, this says that it is equivalent to unrealizability of negation of A, and this simply is equivalent to realizability of A. Right? Just negation. So double negation for sentences, it doesn't matter, right? If I realize double negation, I realize the guy itself. So therefore, I have to realize this guy, which is not possible. So, okay, what's the point? The point is, could be kind of less interesting because I proved, more or less, that something classical is not available in intuitionistic arithmetic. Right? Because we had this soundness theorem, right? And I found two unrealizable things, and therefore I can say that HA cannot prove them, right? So therefore I know that HA, there is some formula A such that HA cannot prove A of X or negation, right? Or also the second guy that I don't want to run. So there is some B such that HA cannot prove that double negation shift, right? So there are some classical things that we cannot really prove in HA. And the reason is that HA is also computable sensitive somehow, that you can do everything computably there, and therefore you can just say that there are some uncomputable things. But who cares, right? These are just some playing with logic. Not very real independence, right? But there are some real independence. The real independence is this. Probably not really today. Is it good or not? Okay, so what's the point? The point is that I said there is something called constructive mathematics, and people cared about constructions, etc. Right? What is construction? Nobody knows. But there is some Russian school of constructivism that's called Russian constructivism. That's that school based on the ideas of Markov and Kolmogorov and the others. The whole idea is that construction means just something computable. It is an algorithm, and therefore something of that sort, right, is there. And then they did serious stuff of developing that Russian style constructivism, the arithmetic, the analysis, right? So for instance, the arithmetic, everything should be, constructible via some recursive things, and therefore, if you have a non-recursive function, you don't accept it, right, as a function, because you cannot just describe it. And for real numbers, for instance, then they think that acceptable real number is the sequence of, zeros and ones or whatever, right? So some infinite sequence of binary things, whatever. And then you can accept it as long as it is recursive, right? Because otherwise, real number is just a very infinite object. I cannot describe it, right? So I have no clue what it is. So that kind of mathematics, whenever it is about arithmetic at least, you can formalize it inside one theory. The theory is HA plus ECT0 plus MP. This is extended Church thesis. 0 means for arithmetic kind of, first order. MP is just Markov principle. So, and everything in Russian style constructivism, you can formalize it here. But the point is that this theory, who knows if it is consistent or not, right? Because I'm not dealing with these generalized things, just CTC0, right? The weaker version Church thesis. So the Church thesis is just the following sentence that says that if you have for all x there exists y, a of x, y, then there exists some e such that for all x, ex halts and a x e dot x. So you see what I say really here, right? This is description of function. It says that if you have a function which is total for any x, you can find y. Then there exists some e, the code of the computation that actually computes that function, right? Computes y. So more or less, I'm saying that all total functions are computable, right? Kinda. And that is just nonsense, right? Classically. So of course, if I add this guy to PA, it is inconsistent. It is inconsistent, sorry, right? You can just find some bad example, right? Some non-computable function or whatever. But that is the base of Russian constructivism. At least we know that HA plus this is less than this theory, right? So who knows if the theory is consistent? And the good news is that it is actually consistent, and you can prove it using that realizability. The only thing that I have to do is actually proving that CT0 is realizable, right? So if I prove, yes.
Just CT.
No. The whole thing is also consistent, but I mean, before anything about realizability, who knows that if the theory is consistent really or not? We know it, but I don't care now because I have to explain things for the extended version and Markov principle. But at least the CT0, I want to show that it is realizable, and since HA is also realizable, the whole thing is realizable, and therefore it cannot be inconsistent. Because if I prove but, then but should be realizable, and that's not the case. Right? I'm providing some sort of weird semantics to prove that something is consistent. But first, something playful, like something classical cannot be provable. But now I'm doing something worse, right? So I'm showing that something really anti-classical is actually consistent here. So how to prove this? Of course, because we live inside the domain of everything is, computable, and therefore, of course, the function should be computable. So find a witness for this guy, right? This is our task. Let's say that E realize this guy, and I have to find something and the realizer, right? So if E is the realizer of this, then what does it mean? It means that for any n, En, right? Okay, probably R. Rn is a pair. The first is the number, the second is the realizer of the thing. So therefore, this E should be what? E, no? The R itself? No. A bit you have to change it, right? Because E should compute the Y, right? And the Y here is just the first, R0. Yes, so R dot N, the projection on 0, is my E. And then the second guy is R dot N on 1, right? Which is the proof of this. And but don't care about this for now. That doesn't matter. So the map is R to this, right? But this is just sorry, lambda n. So you need the code of a function that reads n and computes e of x. And here you need also something that reads n and computes, a realizer for this part, right? So you can construct this. More or less, again, the idea simply is that if you have a realizer here, already the realizer tells you that it is computable, right? Because this y should be computable from x. And how to find the code? The code is already there. It's kind of trivial. Remember again, the guy is anti-classical, but I can realize it. So I gain something, but changing the notion of model that I have. Okay. You don't care about constructive mathematics? That's fine. You care at least about computational content, right? So let's say that, I don't know, whatever. But what if you prove something of this sort? Do I care that what is the, if I have this, the truth of this guy, simply I know that for any x there exists y, but I don't know how to find y, right? If I have a proof of it, depending on the theory, probably I can get more information. So I'm saying that it is provable in constructive theory. Probably I can get more information, right? The more information probably should be that at least since everything is constructive, this y should be at least computable from x, right? So this is called the Church rule. And it simply says that there exists a computable function f, computable, such that, okay, there are many versions, but the one that we need here is this. So this is the standard model again. So that's actually true for any A, for any formula A. But to prove it, you have to change your realizability a bit. I don't want to. Therefore, I just prove it for E-free formulas, right? So then A is the Church rule. Yes. For obvious reasons, right? That simply says that if you can prove the totality of a function, it should be, even in HA, it should be just computable. And of course, again, it is not true for PA, right? Because I'm not saying that A is something low complexity. A can be anything. It can have many universal quantifiers or whatever, right? That is true, as I said, for any A, but I prove it for E-free, and here is the proof. So the proof is HA proves this. Therefore, the guy is realized by some R. Therefore, for any n, R dot n 1 realizes A n R dot n 0. Soundness theory? Okay. And the second definition, right? That you have this. And therefore, for any n, so let's forget about this guy. This is realized And by truth lemma, I have this. Right? But this guy is a computable function, right? It's code applied on n and then projection. So I found my f. The point is that there is more information when you do your constructive proof, right? And but the usual semantics is just, it forgets about everything. But you can keep a bit of the information about computation right there. So let's say that the usual argument when we say that something is provable and therefore it's true is something like that truth is preserved via proofs, right? But what I'm saying is that constructibility in that formal sense is preserved under proof. So you preserve more and therefore you get more at the end. You get all your function. Okay, so these are the things that realizability can do, can prove some independence, but more constructive, can prove, say, can extract some information from the proofs if, again, everything is constructive. So it is just too constructive. But now, since I have a bit of time, I have to say it. So whatever I did is just about natural numbers, right? I started with set of natural numbers, and I said that probably everything, any theorem about it, any statement is constructible via some construction. Okay, fair enough. But is it possible to do the same, not just for numbers, for everything, for any set? Is it possible to develop a set theory, kinda, such that something lurking behind is computable, controlling everything, right? And that would be good because then it means that I can do the same as for just fighting arithmetic for some sort of constructive set theory or for analysis or whatever. And then I have the power to prove independence and also to extract more information from analysis or from any set theoretic construction or whatever, right? So, of course, since topos theory is just some sort of model theory for constructive sets, what I'm saying is that is it possible to lift this realizability idea to a topos?
Just said topos theory is model theory of constructive sets.
Yes.
In what sense of constructive?
No, in the sense that the logic is intuitionistic, meaning the sub-object is just a Heitinger's. So how to construct it, I say about it next time, but today probably I have to say just one thing. And that one thing is what Scott, great Dana Scott, observed. This is the first step somehow. The idea is that if you think about it, the constructions that we had, the realizers, is some sort of weird truth value. So you remember that we started with the H sets, right? So you had some A, and then instead of saying that, either it is true or false, you picked all the times when the guy is true. So now pick all the constructions of it. Why not? Right? So assign, so just work with the same. A is a formula in arithmetic, and then assign to it just all the numbers such that they forces my A. Right? And it is an element in Pn. So you can see that the value is just a subset of n. Some subset of n, right, defined in some way. Fair enough. But Pn is what? It is already a Heiting, even a Boolean algebra, right? So we should say that, okay, probably there is some H set business is going on here, and then we don't see it. That structure, and then that would be good, right? So we unify everything. But at the same time, Pn is just Boolean in the usual sense. But everything we did is just kind of very non-Boolean, right? We refuted the excluded median. Something is bad here. Okay, so how let's say uh-huh. No, in the language of arithmetic, because otherwise I don't know what it means, right? So okay, so let's just investigate more this Pn, right? The elements are in Pn, fair enough, but to have a Heyting algebra, you have to have the order also, right? And also the other constructions, right? What is the order? The order, whatever it should be, is something like that. This must be less than B if A forces B, right? That's a natural order that we have. Okay, so if I translate this notion that we had before to something about the sets, then it would be what? It would be, I say this set is less than the other set if there exists a computable function that transforms any element here to an element there, right? So this is not the usual order on Pn. It's not just a subset. It's more, right? It says that you can have some recursive function, any. It is just about the existence of recursive functions. Okay. And this is the reason that makes everything intuitionistic. Probably it is not the usual Pn. Okay, for now, whenever I say Pn, I mean subsets of n with this order. So the order then is this. So I'm defining a Heyting algebra, hopefully. So the order is this, that some subset S is less than T. These are two subsets of n. If there exists some computable function F, of course, from n to n, but not necessarily total, such that for any x, for any, let's say, n in S, f of n is defined, and it is in T, right? This is just the same definition. So is it a Heyting algebra then? If we are working with some H sets, this should be the Heyting algebra, right? The first problem is that it is not actually a poset. It's a preorder. It is possible that S is less than T, T is less than S, but they are not equal, right? Like even and odd numbers, for instance. There is two functions, one this way, one the other way, but they are not equal. But who
T is comment. Can't you map everything together?
I can? Yes.
So
Yeah, I see. It feels a bit redundant, right? So that you can kill everything to just two values. I see. But yeah, it will be
S reducible to everything.
yes, which is weird, I know. But the point is that I want to generalize things, and then this language fits better, and then later you see that cannot happen always. I see. So with this order, everything is just trivial, right? So if either whatever, I don't want to go there. So you can prove simple. Okay, let me do this. So first, it is not a pre-order. It's a pre-order. It's not a poset, right? Because it is possible that I have two sets. One is less than the other, and the other is less than the first, but they are not equal. So you can just quotient it out, right? And say that up to some equivalence, and the equivalence is that this is less than that, that is less. And then if you do that, then you have that problem that Neil brought in. So the thing is that then you can prove that there are actually two classes, either empty or singleton. Because everything, non so of course empty is less than non-empty. Of course non-empty is not less than empty because there is no function like this. And of course all two non-empties are equivalent because there are obvious functions, right? Just pick one element and constant function. So it is Boolean algebra in disguise, kinda, which is weird because we had some non-Boolean things going on there. Something is bad. We have to think about it. But still, at least this is just a natural thing. Just forget about making it Boolean, by simplification. Just think about this. And then it seems that this is my H, the Heyting algebra, right? After the quotient. If it is a Heyting algebra, just forget about that reduction to Boolean because I want to have it more generalized later. So what should be the structure of the Heyting algebra if it is a Heyting algebra, right? It should have conjunction, disjunction, and implication, and it has. And these are exactly the ones that we had for the definition of the thing, right? So for instance, if I have S and T, so S and T, so this conjunction should be what? It is unique because you have Heyting algebra. If it exists, it should be something unique. But I can describe it via that coding things. It is simply just a set of all R's in N such that R is a pair and R0 is in the first and R1 is in the second. So if you write it down, then you see that really it is exactly in this order. It is exactly the binary meet. And binary join, exactly the one that we described. Implication, probably the Heyting implication is interesting, right? Again, it should be all the codes such that for any S in S, R.S holds and it is inside T, right? So it is different from the usual kind of Heyting implication that we had, right? Like via order and or topology or whatever. It is more computational. This implication really says something about the machines that does something, and then you have pairs, you have etc. So, and probably I have to say that the biggest element is of course n, and the smallest element is of course empty. Okay, whatever. So, okay, I promise this will be the last thing. So the last thing is this. If you think about it, then what I said here, based on what Neil said, that this is kind of just a Boolean algebra 0, 1, it is not that weird. Yes, I know that everything we had was non-classical, but think about it. Here we have just sentences, right? A is a sentence. When A is a sentence, these two guys are equivalent. Right? And also we had that double negation is just doing nothing, right? It is classical. It is more than classical. It is really 0, 1 truth thing, right? Either it is realizable or not. Everything is simplified when everything is a sentence, right? So for sentences, there is no clash really. Everything there was classical. Here everything is classical. Who cares? The problem is when we have parameters, right? We have formula. So you can do the same. Let's say that not just for sentences, for formulas with one variable, right? And then what it should be, the value is what? Of course, it should be a function, right? That reads a number and then picks something in Pn. Meaning that you read your n and then you compute the value, like all the realizers for A of n, right? It's a function. So then the values with one variable really lives in this guy. Right? They are here. Okay. That's not bad. But then what is the order here? So we saw the order is like this there. Let's think about the order here. The order, whatever it is, it should be something like we say AX should be less than BX in this guy. When probably ax, right? And if you think about it, then you see the difference. The difference is that there is one canonical, as we saw, for Pn, there is one canonical order there, right? Subset. And this is not that order. Even if you use that order, on this there is some canonical order. It's the pointwise order, right? But this is not the pointwise order. This is not pointwise. It does not say that for any x, there is a realizer that transforms A of n to B of n. It says that there is a uniform machine that works for any n. Therefore, the order here, if I change it, it would be something like this, that if you have two functions, say, g, f and g in Pn to n, then I say f is less than g when, by definition, there exists some computable code R or whatever, such that for any n uniformly, if f of n is inside, no, sorry, if for any n and for any a, for any r, oh my god, for any a, if a is inside f of n, which is just some subset here, then r dot n, so say pair of na, halts, and it says that I am in G of n. So,
This is the definition.
yeah, this is the definition of the order on this guy. Yes, such that it actually captures the order that we had before, right? So we had this, right? You believe this? Yes. So we have this. Then for any a, for any formula with one variable, I can assign some value for it, right? The value should be an element here that reads one n.
How the evaluate forming some acting out.
In one specific, I think it's yes, right? So I'm transforming the realizability from something is realizer for something else to that pick all the realizers as a set and do whatever you have to do. And if you have one variable, then you have one parameter. That one is a specific case of this. When so let's say that a you have x1 up to xk, this would be n to the k, and that is k0, right? So point is that this order is not simply that order pointwise.
Why are we evaluating formulas?
Because I want to put some, let's say that I have realizability. I want to rewrite it via this.
Classical equivalent.
What do you mean by classical equivalent?
So, value of percent.
Yes.
Something to be variable.
Yes. Yes, the classical version is what? Is that when you have a variable, then you do exactly the same, right? So let's say that in the classical world, when you have a formula A, sentence A, then the value would be 0, 1, right? And if you have a one variable, then what? It should be a subset, and variable comes from a domain M, right? Then it is the value, this guy, right? What it is a subset of M, which is what? Okay, so just to complete it, then this guy would be inside 2 to M. Okay? So what I'm saying, the main point that I want to emphasize is that this order is not pointwise. It is uniform, right? So you can rewrite the whole thing that I said like this, that work with this guy, these guys, with k variables, and then put some order like this right? The uniform version on that. 1, 2, and then 3, check that if it is a Heyting algebra, the whole thing is a Heyting algebra, and it is a Heyting algebra, actually, via exactly those constructions. And in this case, since it is not just pointwise, it does not reduce itself to just the Boolean 0, 1, right? It is something else. And this is the reason that for formulas, we have the failure of excluded middle, but for sentences, we don't, right? But anyway, that gives us the idea that how to generalize it, and I want to explain it, but the structure is something like this, right? That if you want, yes, just one sentence, that how to generalize the idea, we had H sets, right? So if I want to have some effective sets, they should be what? They should be one set, one relation R, right? But then the values, of course, as before, they live inside Pn. So you can read any element here as the witness or realizer of the equality of the things, with some conditions that we come back to it. But the point is that this R is actually an element in Pn to x times x, and you have to think inside this guy, right? This is the values, the word of values for variables. So my main point, for H sets, you fix your H, and everything is just pointwise in H, right? You have just the value for one variable would be, as we saw here, H to X, right? Two variables, H to this. Here it seems that for any different X, you need different thing. It's not uniformly constructible via Pn via your H, right? For any X, you have different, yeah, there is some connection between them, etc. But the point is that you have to do uniformly everything, right? So there is a change. So point is that then we cannot rewrite probably the whole thing as H sets. It is a generalization somehow. Not that really. So it is another sort of thing. H set is another one, and both of them are instances of one generalized way of thinking that we have to talk about. So next time then I talk about effective sets, whether it is in next week or after the year.
And this will come back to opposites.
Yes. So yes. So if like H sets, everything was. So now you are so interested in topos, right? So if you have H sets, then you can have a topos, right? For fixed H. The same is here. So if you work with natural effective sets in some reasonable sense, with some morphisms, etc., then it is also a topos. That's called the effective topos. That encodes the computable word, if you like. Okay. Thanks. No questions? This is completely different. So one of the things that I will prove is that effective top. Okay. So first, on the very obvious level, the effective topos is a topos, but it is not grotesque. Therefore, obviously it has nothing to do with it. But the point is that it is kind of, the whole thing that I try to explain is that the sheaf construction comes from the notion of time. This comes from the notion of construction. So these are two really different things. It should be possible to unify them, right? To construct toposes based on any notion of temporal construction, right? But they are so different. Also in practice, so you can. So for instance, these effective topos is kind of useless when you want to do something for classical set theory, because time is something meaningful for classical set theory, right? Of course, in set theory, you don't have any time, right? But you can think of time as we did for forcing, like the informal, the incomplete information, right? That you have and you complete it next, and next, right? So there is some sort of classical reading of things, and therefore that sheaf structure is useful to prove independence in classical. Here, if you think classically, then it collapses just to set. So there's nothing to do. And as you can see here, right? So if you forget about, if you restrict yourself to negative formulas, then it is just classical, right? So it is really constructive. You cannot use it for anything non-classical, and therefore this is the difference between this guy and the sheaf world. Of course, you can develop any sheaf theory inside any topos. So therefore, it is possible to have sheaf theory relative to this guy, but this is just something different, right? It's another story. Okay, that's it.